Hello, this is Physics Paper 2, February, March 2023. So I would like to take you through this paper. Let's start with question number 1. Part A, underline all the SI base units in the following list. The base units was, this is amperes. Coulomb is a derived unit. Current is not a unit, current is a quantity. Kelvin is a base unit. Newton is a derived unit. So the answers here is ampere, amperes, and Kelvin. Now, a toy car moves in a horizontal straight line. The displacement S of the car is given by the equation S is equal to V squared over 2A, where A is the acceleration of the car and V is the final velocity. State two conditions that apply to the motion of the car in order for the above equation to be valid. If you look at this equation here, this equation is derived from this kinematic equation, that is V squared is equal to U squared plus 2A plus 2AS. Now, what's happening here is that for us to get this, U, the initial velocity U must be 0. So if initial velocity U is 0, that means that we have V squared is equal to 2AS. And therefore from there we get S is equal to V squared over 2A. This gives you a condition that the first condition here is that the initial velocity U must be 0. Initial velocity U must be 0. Then the second condition is that as you look at this equation here, this equation applies if the value of the magnitude of acceleration remains constant. It is not applicable where there is a changing value of acceleration. So acceleration, so the magnitude of acceleration remain constant. The magnitude of the acceleration remains constant. But then some of us, we also know that F is given by ma, meaning that for the same body, even the resultant force should remain constant. So either of them is right. But see, an experiment is performed to determine the acceleration of the car in part B. The following measurements are obtained. So we have S is given by 3.89 meters plus or minus 0.5%. Then we have V as 2.7 meters per second with a percentage error of plus or minus 0.8%. Calculate the acceleration of the car. So from here, we know that from this formula, S is given by V squared over 2A. So to make A the sum of the formula, so A will be V squared over 2S. So what you need to do is here, because we want A, just interchange this and this. You don't need to worry about that. So now from here, A is given by V squared over 2S. V squared, so that is 2.75 squared divided by 2 times 3.89. And that gives us 0.97 into two significant figures. Roman 2, determine the percentage uncertainty to the two significant figures of A. So you can able to see clearly that so the percentage uncertainty in A will be given by percentage uncertainty in V, but you can able to see because V is squared, that means that we multiply the percentage uncertainty in V by 2, multiply with the N, then we add to the percentage uncertainty in S. So all this is provided. So percentage uncertainty in V is 0.8, so that will be 0.8 times 2 plus 0.5. The percentage is already calculated there, so we just get our answer 2.1 into two significant figures. Roman 3, use your answers in C, Roman 1 and C, Roman 2 to determine the absolute uncertainty in the calculated value of A. Now, percentage uncertainty in A is given by the absolute uncertainty in A over the value of A times 100%. So if we have this, it therefore means that the absolute uncertainty will be this percentage uncertainty, which is 2.1. So 2.1 over 100 times the value of A, which is a 0.97. This gives us 0.02037, but into one significant figure, we get 0.02, which is meters per second squared. Question number 2. A motor uses a wire to raise a block as illustrated in the figure 2.1. We have a motor here, the wire. So X, Y, and Z. The base of the block takes a time of 0.49 seconds to move vertically upward from level X to level Y at a constant speed of 0.64 meters per second. During this time, the wire has a strain of 0.0012. The wire is made up of metal of Young modulus 2.2 times 10 power 11 Pascal and has a uniform cross section. The block has a weight of 1.4 times 10 power 4 newtons. Assume that the weight of the wire is negligible, but A, calculate Roman 1, the cross-sectional area of the wire. So we know that Young modulus is given by stress over strain. We have been given strain, we are looking for A, but you know very well that stress is given by force per unit area. So therefore from here, we have Young modulus given by F over strain times cross-sectional area. And because you're looking for cross-sectional area, this applies that A, cross-sectional area A is given by F over strain times the Young modulus. And so we just do the substitution. So therefore A is equal to the force, which is the weight, that is 1.4. So for this particular part here, you see what is happening here is that the block is moving at a constant speed. If the block is moving at a constant speed, it means the tension in the wire T is equal to the weight. Because the body is moving at a constant speed. Therefore, the resultant force is 0. So that's why we're using the force as the weight. So 1.4 times 10 power 4 Newton divided by, that is the strain, 0.0012 times the Young modulus, which is 2.2 times 10 power 11. So using a calculator, this gives us 5.3 times 10 power negative 5 meters squared. Roman 2, the increase in the gravitational potential energy of the block for the movement of its base from X to Y. So we need to calculate the increase in gravitational potential energy from X to Y. So we know that the increase in gravitational potential energy, the change in gravitational potential energy is given by mg times change in h. So if you look at this, we have mass, we have g, but we don't have h. So we can able to find the change in h. Change in h, that is from x to y, that is equivalent to the distance covered or distance moved from x to y. And that distance moved is done so in 0.49 seconds at a constant speed of 0.64. That means you can able to find h. So h will be equal to 0.49 times 0.664. That is 0.664 that is 0.3136. So from here, you can able to see clearly that mass is weight over gravity. Therefore, weight is just mg. So this value here, mg, is the weight, which we already have. So that is 1.4 times 10 power 4 newtons. Then you multiply with the change in displacement, or the value of the distance, that is 0.3136, which gives us 4,000. So 4,390.4 joules into two significant figures. That would be 4,400 joules. The motor has an efficiency of 56%. Calculate the input power to the motor as the base of the block moves from X to Y. Now remember, by moving the block from X to Y, that is the useful work that is being done. And that useful work done is what you have calculated there, is the change or increase in the gravitational potential energy, which is 4,400 joules. So we know that efficiency is given by the useful power over the total input power, and you multiply this by 100%. So therefore it means that 56%, or 56 over 100, is given by the useful power. And how do we get useful power? Remember, the time taken is 0.49 seconds. So therefore the useful power will be 4,400 divided by the time, 0.49. 8979.6, something like that. So therefore we have 8979.6 divided by the value x times 100%. We already have it this side here, and therefore from here, x, which is the input power, will be 100 over 56 times 8979.6. That will give me, into two significant figures, 16,000 watts of the input power. In other words, someone can do it this way, because we know that 56% is the useful work done, or useful power. So we know that after calculating the power, which is this, we can able to say that what 56% is equivalent to 8979.6 watts. How about 100%? That will also give us the answer, which is 16,000 watts. Now, part C, the base of the block now has a uniform deceleration of magnitude 1.3 meters per second from level Y until the base of the block stops at level Z. Calculate the tension T in the wire as the base of the block moves from Y to Z. Now, if you look at the diagram here, as it is moving from Y to Z, we are being told that there is a deceleration. That means acceleration there is negative 1.3 meters per second squared. For the body, for this block here to be decelerating, what does it mean? Remember, there are two main forces here. There is tension acting, which is in the wire, and there's also the weight that is acting downward, which you have its value here, 1.4 times 10 power 4. Now, when there's acceleration, it therefore means there's a resultant force, and because the body is decelerating upward, it therefore means that the weight must be greater. So the weight must be greater than the tension. That is why it is now decelerating. So the difference here, which is weight minus tension, gives us the resultant force. And the resultant force from Newton's second law, if derived, is equal to M is equal to MA. So therefore, weight minus tension gives us MA. Therefore, tension will be weight minus MA. So therefore, we just need to calculate. So tension will be equal to weight, but that is 1.4 times 10 power 4 minus M, mass. Remember, once again, mass M is given by W over G, and W is 1.4 times 10 power 4. So that will be 1.4 times 10 power 4. To find M, this M here, we divide by 9.81. We multiply with the acceleration, which is 1.3. 1.2 times 10 power 4 newtons. Remember, I mentioned earlier there that acceleration is negative 1.3 because it is decelerating. Now this negative just shows the direction of the resultant force. Now part B, the base of the block is at levels x, y, and z at times tx, ty, and tz respectively. On the figure 2.2, sketch a graph to show the variation with time t of the distance d of the base of the block from level x. The numerical values of d and t are not required. Now let's see. So from the diagram, from x to y, the block here is moving at a constant speed. Then from y to z, the body is decelerating. So if you plot a graph of distance against time, remember the gradient there, m, will be change in distance over change in time, which gives us speed. So the speed has to be constant. For speed to be constant, so there must be a straight line from the origin. I want to be accurate. So a straight line from the origin until where we have to. So please know that this must be a straight line. Then to show that it is decelerating from ty, then the gradient has to decrease. So the gradient from here will have to decrease, and then stops at tz, something like that. So it has to be a straight line from the origin until where we have ty. Then from ty, the gradient decreases to show that the body is decelerating. A uniform beam AB is attached by a hinge to a wall at the end A as shown. So you can able to see the diagram. So we have the hinge there, which is acting as the pivot. We have the beam whose weight is W. There is a block there that is placed, which is weighing 12 Newton. There is tension supporting the hinge, and that is in anti-clockwise direction. So we have been given the information about the diagram. The beam is held horizontally and equivalent by a string attached between end B and a fixed point C. The string has a tension 17 Newton as indicated in the diagram, and the angle to the horizontal, which is 50 degrees. Set two conditions for an object to be in equilibrium. Now, for an object to be in equilibrium, the resultant moment must be equal to 0. Now, some of the students always make a mistake and mention that the moment must be equal to 0. That would be wrong. So the resultant moment must be equal to 0. What does it mean? It means that the sum of clockwise moment about a point must be equal to the sum of anti-clockwise moment about the same point. So the best is that the resultant force in any direction must be equal to 0. Now, show that the vertical component of the tension in the string is 13 Newton. So the vertical component, if I may sketch the diagram here, you can able to see. So I draw the tension as the hypotenuse, then I draw this, the vertical component, which is that, then allow me to draw the horizontal component. So this is a 50 degrees. So if you're looking for the vertical component of the tension, that means we are looking for this part here of the force. So that, if here is 17 Newton, then we have to use SOHCAHTOA. We have to apply SOHCAHTOA here. SOHCAHTOA, which we're able to see the angle here, 50 degrees, is opposite to the length that the component that we're looking for, and that is Fy. So from here it means sine of the angle, that is sine 50 degrees, is equal to opposite, which I'm calling Fy or Ty. I think let's use T because it's tension. So Ty of the hypotenuse, which is 17. So that means that Ty will be equal to 17 sine 50. So 17 times sine 50, that gives us 13.022. So therefore we have shown that that is 13 Newton. Now you need to know that a question that asks you to show, you must clearly show what you're doing. That is when you're able to earn a mark for this, but just writing the answer will not give you a mark at all. So by taking moments about and A, calculate the weight W of the beam. Now we look at this diagram here, we realize there are more than one forces acting on this body here. If you assume that W is the only force acting on this beam here, then you can able to see it will able to rotate the beam in a clockwise direction. Same to 12 Newton. So therefore it means 12, the force W and the force 12 Newton, they are both acting in a clockwise direction, and therefore we will get their moment. So clockwise moment. Remember part C here, we are applying the principle of moments. So therefore W, the whole beam, because it is a uniform one, so there, if it is uniform, it means that the center of gravity is at its center, geometrical center. So if from A to B is 0.35 plus 0.15, which is 0.5, therefore it means that W is acting at 0.25 from the pivot, which is at point A. So therefore the moment to the W is, so that is W times the distance, which is 0.25. We add to the 12 Newton times the distance to the pivot, and the distance to the pivot, that is 0.35. 0.35. This should be equal to the anticlockwise moment, which is provided by the vertical component of the tension. Why are we using the vertical component? Remember, moment is the product of force times perpendicular distance. The distance here must be perpendicular to the force or the line of action of the force, and must be from the pivot. So that is why we are going to use 13 Newton. So the 13 Newton is vertical, because you can able to see this is the component of the force, which is vertical. So it will be acting along this. That is 13 Newton here. So 13 Newton times 0.5. So 13 Newton times 0.5. Therefore, this means that W will be equal to 13 times 0.5 minus 12 times 0.35, and all of this divided by 0.25. So what do we get? 9.2 newtons exactly. Part B, calculate the magnitude of the vertical component of the force exerted on the beam by the hinge. So let's look at the diagram once again. So if there's an upward force here by the hinge acting upward, now we apply, remember for this question, part C, we have applied this condition here. We have applied this condition that the resultant moment about a point must be equal to 0, meaning clockwise moment is equal to anti-clockwise moment. To get the force or the support at A, which is acting upward, now we apply the second condition, where we say that the resultant force in any direction must be equal to 0, meaning the upward force here for this diagram should be equal to the sum of the downward force. So if I call that force F, it therefore means that F plus 13 is given by, is equal to the weight W, 9.2 plus 12. So this gives us a value of, so F here will be 9.2 plus 12 minus 13, which is 8.2 newtons. Now the block is now moved closer to end A of the beam. Assume that the beam remains horizontal. State whether this change will increase, decrease, or have no effect on the horizontal component of the force exerted on the beam by the hinge. Now, if we look at this question here, let's look at the diagram. So if the 12 Newton weight, the block is now moved closer to NA. So if the block is moved closer to NA, what does it mean? It means the total clockwise moment acting on the beam will decrease because of the decrease in distance here. If the clockwise moment decrease, it therefore means that what the anti-clockwise moment must decrease as long as this beam remains horizontal. If that is the case, remember the downward force and the upward force will still remain the same. But for the tension to decrease, it therefore means that the horizontal component of the tension must decrease. The force exerted on the beam by the hinge will also decrease. Question number 4. Two blocks slide directly towards each other along a frictionless horizontal surface, as shown in figure 4.1. The blocks collide and then move as shown in figure 4.2. So this is about momentum. Now, block X initially moves to the right with a momentum of this 0.37 kilograms per second. Block Y initially moves to the left with a momentum of 0.65 kilograms per second. After the blocks collide, you can able to see on the diagram. Part A, block X has an initial kinetic energy of 0.30 joules. Calculate the mass of the block X. Now, we have two things here. For X, we have been given momentum of X, which is 0.37 kilograms per second, and we have its kinetic energy, which is 0.30 joules. Now, kinetic energy is given by a half mv squared. Momentum is given by sorry for that. Momentum is given by m. So from here, we can actually, connect kinetic energy and momentum. One of the easiest way is this. Kinetic energy is mv squared over 2. So what I can do here is to multiply up there by numerator by m, then this one here by m. So m over m is 1, but that will give us m squared v squared over 2m. So therefore, that means that kinetic energy, because momentum is mv, but we have here m squared v squared, it therefore means that kinetic energy is v squared over 2m. If I'm looking for the mass will be p squared over 2 times kinetic energy, which is 0.37 squared over 2 times 0.30. Get 0.23 into two significant figures, 0.23 kilograms. Now, determine the magnitude of momentum of block Y after the collision. So we look at the diagram here. You decide. So if for X, if we take the direction of X, which is to the right, to be positive, that means you'll take the direction of Y initially to be negative. That means momentum before collision will be positive 0.37. So 0.37 plus negative 0.65. There is momentum before collision, which gives us negative 0.28 kilogram meters per second. Then momentum after collision should be equal to momentum before collision. Now X and Y after collision, they are moving to the left, which we have taken to be negative. That means we'll have Momentum before collision is negative 0.28, which should be equal to negative 0.13 plus negative p, where p is the momentum of y, that is after the collision. So from here, we'll be able to get negative 0.15 is equal to negative p. Therefore, momentum will be 0.15 kilogram meters second. Block X exerts an average force of 7.7 Newton on block Y during the collision. Calculate the time that the blocks are in contact with each other. So we want to see how force, time are related, but then of course that is through momentum or impulse. So we know that the resultant force is given by change in momentum. Change in momentum. So for this case, we are dealing with X over the time taken for that change of momentum during the impulse. So changing momentum for X, let's look at the diagram. Now X, initially X is moving to the positive direction, but then after the collision, it is now moving in the negative direction. Therefore, we will give this to be negative. So we'll have, so before collision, it is 0.37. After collision, we have negative 0.13. So therefore, that means change momentum will be negative 0.13 minus the initial, which is minus 0.37, divided by the time taken, t, and this should give us the resultant force, which is 7.7. So therefore, from here, this should be, so that should be 0.5. So t should be equal to negative, which we'll about to ignore, negative 0.50 over 7.7, 0.065 seconds. Okay. Part 5A. A microphone and a cathode ray oscilloscope, CRO, are used to analyze a sound wave of frequency 5000 Hz. Now the trace that is displayed on the screen of the CRO is shown in the figure, which you can go to see. Now determine the time-based setting in seconds per centimeter of the CRO. Now time-based, this one here we're looking for the X displacement, sensitivity, Y gain sensitivity. We look at the vertical displacement, but this one here we are looking at the X displacement, horizontal displacement. So we've been given a scale here. So for these 5 small boxes is considered to be 1 centimeter. We have been given a frequency here. So with the frequency, we can able to find the time period. The time period is equal to 1 over frequency, that is a 1 over 5000, which is equal to 2.0 times 10 power minus 4 seconds. So it means that the time period is given that. So time period, if we consider this, that is from here to here, that is 1 wave. So that is the time taken for 1. So for 1 complete wave, there are these large boxes which have, there are 4 of them, which have 5, so 5 small boxes. From here to here, there are 4, meaning that the time-based setting will be 2.0 times 10 power minus 4 seconds divided by 4. That will give me 5.0 times 10 power minus 5 seconds per centimeter. The intensity of the sound detected by the microphone is now increased from its initial value of I to a new value of 3I, where I is the intensity. The frequency of the sound is unchanged. That means the wavelength change or the time period doesn't change. Sorry. Assume that the amplitude of the trace on the CRO screen is proportional to the amplitude of the sound wave. If that is so, then we remember, or you can able to recall, that pi is directly proportional to a squared. This implies that if you talk about if we consider the amplitude that we are seeing on the screen to be a1, so therefore we'll have a1 to be direct proportional to the square root of I. So for second amplitude, I is now 3I, and therefore, so A2 is direct proportional to the square root of 3. Square root of 3 is 1.7, so that would be 1.7 of I, meaning that amplitude 2 is equal to 1.7 of the first amplitude that you're seeing. So if you're going to do the sketch, then we consider this. So A2 is going to be 1.7 times that of A1. So if I look at this one here, for the amplitude, I'm seeing from the mean direction, we have 1, 2, 3, 4, 5. So the amplitude here, which I'm considered to be A1, as small as 1 centimeter. 1 centimeter. That means amplitude 2 will be 1.7 centimeter. So that means from here, so this is 5, 6, 7. The amplitude will be here. Then this one also will be somewhere here. Then this also will be here. So we do a sketch. Remember, it doesn't change. Sorry, it has to pass through this particular point. Something like that. So just make yours smooth, but the amplitude must be clearly indicated at 1.7. Okay, good. Now we look at an arrangement for demonstrating interference using light is shown in the figure 5.3. So you're able to see we have the slit separation is 3.6 times 10 power minus 4 meters. The screen is here. That is 630 nanometer. Okay. The wavelength of the light is given. Light is incident normally on the double slit. The separation of the two slits is given. The perpendicular distance between the double slits and the screen is B. Coherent light sources, light waves from the slits from an interference pattern of bright and dark fringes on the screen. The distance between the centers of the two adjacent bright fringes is 4.0 times 10 power minus 3 meters. The central bright fringe is formed at point P. Roman 1, explain why a bright fringe is produced by the waves meeting at point P. Now, because P is where we're going to have the central maximum being formed, meaning if that ray of light traveling from there to this particular point, they will also be traveling at the same particular point. It will form like a contour triangle. So it means if I call this one here slit 1 and this is slit 2, the truth is that slit 2P, this distance minus slit 1P will give us 0. That means the path difference here will be 0 wavelength. And remember, if the path difference gives us n when they're meeting at that particular point, so we're going to have constructive interference. So the reason here is that the path difference here is 0. Therefore, there is constructive interference. there is constructive interference at point P. Calculate distance D. So this is given by, lambda is given by AX over D, meaning that D will be given by AX over lambda. So this will give us 3.6, which is provided 3.6 times 10 power minus 4 meters, multiplied by X, which is 4.0 times 10 power minus 3 meters, divided by the wavelength, which is 630 nanometer, that is times minus 9. So therefore, with calculating, D will be given by 2.3 meters, the two significant figures. Okay, the wavelength lambda of the light in B is now varied. This causes a variation in the distance x between the centers of the two adjacent bright fringes in the screen. The distance D and the separation of the two slits are unchanged. Okay, so sketch a graph to show the variation of x of lambda from 400 to 700 nanometer. Numerical values are not required. Now, look at this. So lambda is given by AX over D. We are plotting a graph of X against lambda. That means that X will be equal to D over A of lambda, meaning this becomes our gradient. So because gradient is constant, so therefore X. So if you're plotting X, remember for this particular point here, the value of X won't be 0. So, and they're direct, they're proportional. They are proportional. So they are proportional. Therefore, we will have a graph that is cutting with a positive value of X straight, because they are proportional. So X cannot be 0 here. That's why we don't start from the 0 400 or 400 0. Now, question number 6. But A, define the potential difference across a component. So potential difference, PD, is energy transferred. Remember, this is across a component, so energy transferred, we can say from electrical to other forms of energy. For example, if it is a PD across a bulb, it will be from electrical energy to light or thermal energy. So it's from electrical to other forms of energy, per unit charge. Or just to make it short, we can just say that this is the energy transferred across a component per unit charge. It will be all for 1 mark. The variation with potential difference B of the current I in a semiconductor diode is shown in the diagram. Describe qualitatively. Qualitatively means we don't need the values. Roman 1, the resistance of the diode in the range B is equal to 0 to B is equal to 0.25. Now, here, the resistance between these particular values here, you can able to see clearly that the value of I is 0. Resistance from Ohm's law is given by V over I. And if I is 0, it means the value of resistance is very, very large. So we can say that is infinity. The resistance is infinity. Maybe at infinite value. Or you can say that it's very, very high. It is very high. Infinite. Now, the variation, if any, in the resistance of the diode as V changes from V is equal to 0.75 to V is equal to 1.0 voltage. So as voltage increases, you can able to see a small change in voltage now cause a very large change in current. That means there is a decrease. So resistance decreases as V changes or increases from 0.75 to 1. But see, a battery of electromotive force, that is EMF 12 volts, and negligible internal resistance is connected to a uniform resistance wire XY. A fixed resistor and a variable resistor is shown in the diagram of that. Okay. All right. The fixed resistor has a resistance of 5.0 ohm. The current in the battery is 2.7 amps, and the current in the fixed resistor is 1.5 amps. That means that the current along the resistance wire XY will be 2.7 minus 1.5, which will give us 1.2. So it means 1.2 amps is flowing through the XY resistance wire. Calculate the current in the okay, we already have that. So that will be 2.7 minus 1.5 amps, which will give us 1.2 amps. Determine the resistance of the variable resistor. Determine the resistance of the variable resistor. Now remember, look here. The variable resistor and the 5.0 ohm resistor, they are in series, but both of them are in parallel to XY and parallel to the battery. That means the potential difference across 5 ohm resistor and the variable resistor is 12 volts. But the sum of potential difference across the 5 ohm and the variable resistor should be equal to 12. Hope you understand. So the potential difference PD across the 5 ohm resistor is given by current. You know that voltage is given by IR, or PD is given by IR. So therefore, this will be 1.5 times 5, which gives us 7.5 volts. Therefore, the PD across the variable resistor will be 12 minus 7.5. 12 minus 7.5. That will give us 4.5. So there is a 4.5 volts. 4.5 volts. So therefore, the resistance, which is given by V over I, that will be 4.5 volts divided by current. The same current flowing through the 5 ohm will flow through the variable resistor because they are in series. There's no other way where the current, this current can go to flow. So that will be 1.5, which gives us 3. But into two significant figures, we put 3.0 ohms. Good. Now, Roman 3, wire XY has a length of 2.0 meters. Point Z on the wire is a distance of 1.6 meters from point X. The fixed resistor is connected to the variable resistor at point W. Determine the potential difference between points W and Z. Let's look at the diagram. So we want the potential difference between them. So for us to do that, let's draw this so that you can able to see the potential difference between X and W and Z. Now, for this question, what we know is that from Ohm's law, voltage and resistance are directly proportional across. So voltage across a component is directly proportional to the resistance or the potential difference that matter. And we also know that resistance is also directly proportional to the length. This implies that voltage also directly proportional to the length. Meaning, if I want to find the potential difference between XZ, the potential difference between XZ will be the length XZ is provided. That length is provided us. So point Z is on the wire at a distance of 1.6. So that is 1.6. So meaning I can find that will be 1.6 over total length, which is 2, times the total voltage. Remember, from X to Y, the potential difference is 12 volts. It's parallel to the battery. We multiply by 12. There's 1, 6, 6, 6. So this gives us potential difference of 9.6. So remember, if we draw the line from Z to Y so that we can able to find the potential difference, this part here is 9.6 volts. This one we already calculated, which is 7.5 volts, meaning the potential difference between W and Z will be 9.6 volts minus 7.5 volts, which is equal to 2.1 volts. That is the answer. Roman 4, the resistance of the variable resistor is now increased. The resistance of the variable resistor is now increased by considering the current in every part of the circuit. State and explain whether the total power produced by the battery decreases, increases, or stays the same. So we have to analyze this so that it can be able to give us 3 marks. Now let's look at this diagram here. So if you look at this diagram, we can be able to see clearly if the resistance of the variable resistor is increased. If that R is increased, it means the current flowing through this fixed and the variable resistance will decrease. So the current flowing through the variable resistor, of course, and the fixed resistor will decrease, while the current flowing in the resistance wire XY will remain the same. Will remain the same. So what does it mean? It means there will be a decrease. That means that the current flowing through the battery also decreases, and because power dissipated or produced given by IP is the same, but current has decreased. Therefore, it means that the power produced by the battery will decrease. Power produced by the battery will decrease. Okay. So the last one, number 7. Part A, nuclei X and Y are different isotopes of the same element. Different isotopes means they have different neutrons. Nucleus X is unstable and emits beta plus particle to form nucleus Z. By comparing the number of protons in each nucleus, state and explain whether the charge of nucleus X is less than, the same as, or greater than the charge of nucleus Y. So nuclei X and Y are isotopes. So if they are isotopes, that means they have the same number of protons, the same number of charge. That therefore means that they will have the same. So nucleus Y has the same number of charge as that of X. Now, if you look at nucleus Z is formed when nucleus X undergoes or emits beta plus. So if it emits beta plus, it means Z is going to have less number of protons than X, because let's assume this way, what is happening. So let's say this one has M here, this is A, it's emitting beta, beta plus to form Z. So beta plus, this is a +1 here, 0 here. That means if here A, here will be A minus 1. See this particular part here. That means that nucleus Z will have less number of charges, will have less than X, or X has greater charges than Y. So therefore, so nucleus Z has less than that of XY, because X has one more proton, it has more proton number than Z, so that you can able to get the 2 marks. Now, part B, hadrons can be divided into 2 groups or classes. That is P and Q. Group P is baryons. That means group Q is mesons. Describe in general terms the quark structure of hadrons that belong to group Q. So 1 quark and 1 antiquark. So mesons is made up of 1 quark, 1 quark and 1 antiquark, while baryons is made up of 3 quarks. So that is it. Thank you for watching. If you have any comment or any question from what you have done today, please comment it down there so that we can able to correct it. If there's any mistake that I've done or I've made, please raise it so that we can able to correct it. Thank you for watching. See you in our next video.